Hello, Math 126 fans. Somebody's asking me a question about lines and planes that makes me think there needs to be a little bit of a review of our happy situations. So let's review an important thing. So the student is asking me something about lines and planes being perpendicular. The moment you see the word perpendicular and you're talking about a plane, we should be happy. Because if I have a line that is perpendicular to a plane, that's why I always like, when I'm drawing a plane, I always like to draw this picture. A plane is characterized by the fact that you have this normal vector. It is perpendicular to the plane. A line is characterized by having a vector that points in the direction you're going. We talked about how there are three situations we really like. If you have two lines that are parallel to each other, then you can use parallel vectors. If you have two planes that are parallel to each other, I call these the three happy situations, then you can use normal vectors that are parallel to each other. And I said our third situation we like is when you have a line and a plane that are perpendicular. Those are the only three scenarios where you end up with parallel vectors. These are parallel, these are parallel, and these are parallel. Now the question the student is asking me is, they're saying, why are you assuming these are parallel? So that's what I'm trying to answer. They should be parallel, they're not perpendicular. But the question says perpendicular, but the normal is perpendicular to the plane. So if the normal is perpendicular to the plane and the line is perpendicular to the plane, they are parallel to each other. So you need to remember these three key situations. So anyways, the first observation of this question is that I want the normal for the plane to be parallel to the direction vector for the line, which is 1, 3, -2. Again, I know that that says parallel and that says perpendicular, but that's about lines and planes. So if the line is perpendicular to the plane and the normal is perpendicular to the plane, then they're parallel. Okay, so that's that moment that students are getting confused about. Okay, so now your job is to try to describe this vector v. And that's really the other part of this question. There's sort of, so let's separate. This was the idea. That's one. I'm going to move some so I can see my screen better. So that's the idea. So sort of talk about the principles you would need to do such a question. You would need to remember how to tell if vectors are parallel. Now, two vectors are parallel. If you put them tail to tail, that means they are scaled multiples of each other. So that means that v is some multiple of this vector. So sometimes I like to change. I've done this question before in class. I'm doing it again, but in a slightly different order to sort of emphasize a few things. So my challenge in this question is to figure out what the direction vector looks like, and then set the first component equal to k, the second component equal to 3k, and the third component equal to -2k, and see if that's possible. If so, I'll figure out what k is, and then I'll know what's in those question marks. That's the goal of the question, because that's what it means for two vectors to be parallel. You can also take their cross product. So another approach is to do the cross product of v and 1, 3, -2, and figure out when it's equal to 0, 0, 0. Because if two vectors are parallel, their cross product is 0. But I would say that's a less optimal solution. It takes longer. This is a faster solution. Those are two different ways to check if two vectors are parallel. All right, last piece of the puzzle. How do we get v? So that's the other challenge of the problem. So a tangent plane we know looks like this, where there's something here, x minus some number, there's something here, y minus some number. So the other challenge of the question was, well, that doesn't look like a normal vector. Typically when you write down the equation of a plane, back when we were learning it, so yes, several things do come together here. We would write it this way, and the 3 numbers in this spot were our normal vector. Oh, and I apologize. I think I've been labeling incorrectly. It's the n we don't know. The v we knew. So apologies. Trying to be as clean as I can, but I didn't do it. We knew the v. The v was 1, 3, -2. And we are trying to find this n. We're trying to find the point. But if we find the n, we will know the point. Okay, so this was this thing where, all right, I got to move everything to the same side. So I'm going to move this over, move this over. There's a 1 here, because there's a 1 here. But I need to figure out the other pieces. So the other pieces, this is going to be 2x, whatever I get when I plug in the x value to 2x, because that's the partial with respect to x. This is going to be -2y. So I personally would like to call the point, the x's and the y's are fumbling me up, so I'm going to call the point ABC, this point we're trying to find. Okay, so this would be 2a, and when I move it to the other side, it's going to be -2a. This is going to be -2b, and when I move it to the other side, it's going to be 2b, and I have it. -2a, 2b, 1. This is the normal vector at any point on the surface, and now I can insert that here. So I have -2a, 2b, 1 equals k, 3k, -2k. So -2a is 2k, 2b is 3k, 1 is -2k. That means k is -1/2, and we can plug that in to find a and b. So what happens? You get -2a is -1, so a has to be 1/2. And you plug this in, you get 2b has to be -3/2 divided by 2. You get b has to be -3/4. Find a point on the surface whose tangent plane, so at that point when x is 1/2 and b is -3/4. So let me know if I made a mistake in there. But the key conceptual things were understanding this idea, understanding what it means for two vectors to be parallel, and finally knowing what the tangent plane looks like and using the tangent plane to find a normal vector. All right, hope that clears up that piece. Let me know if you have follow-up questions.